Hi, welcome to Music 302, Engineering section. My name is Wiley Ross, Recording Studio Coordinator for our recording studio here in the School of Music. You can find us in the basement of the music building at room 57. So make sure that you check out the webpage. In addition to 302 sections, you have other sections of how to access the studio, which if you're a musician or a producer, you can do and even get some free time. In fact, I think there's going to be an assignment to do a jingle if you want for extra credit, and you can use the recording studio for that. I also have a YouTube channel that I'm going to be adding more stuff to. Right now there's a few tutorials on how to do various things that are related to the class. So please check that out. And if you have any requests, let me know. This class is best learned by doing. And you can do some of the things that I talk about in class simply by using your computer and downloading some software. So here's some software that you can download. Some of it's free. Some of it is a 30-day or 60-day trial. All these work really well. You may also have software that you can use to do some of the things that I lecture about. And I highly encourage this because this is the way you really learn something by doing. Our first lecture is going to be on sound and perception. First, I like to start with the definition of sound. This is my own definition. The perception of acoustic stimulus created by a vibration in air. This vibration moves the air, resulting in air pressure changes, and that in turn, of course, gets transmitted through space to our eardrums, and we hear the sound. So at the bottom here, we have a little illustration, and as you can see, what's happening here is the red bar is moving, and that represents something vibrating. And those black dots represent air molecules. And as you can see, as the red bar moves against the air molecules, they compress together, making a high pressure zone. And as it pulls away from those dots, it makes the dots go further apart, representing a low pressure zone in the waveform. And when we talk about waveforms, we're talking about a wave that has what we call a peak and a dip. So every wave has a cycle that starts out from no sound pressure to high sound pressure, and then going down from that to low sound pressure, and then back up to zero again. So that's what is being represented here in the diagram. So the simplest kind of wave, sound wave, is what we call a sine wave. And a sine wave is a pure tone consisting of only one frequency, but it has amplitude and wavelength. Amplitude simply refers to the intensity. And actually the amplitude is not only just positive, it's also negative. So I should have written probably the negative portion there for the bottom part of the wave. So amplitude is simply intensity, or how loud it is. Wavelength is how long it exists in space. And yes, sound waves can actually be measured with length. The longer the waves tend to be lower frequencies, the shorter waves, high frequencies. That's a 1 kilohertz sine wave. And we should also know that sound has a certain velocity or speed. In air, the speed of sound is approximately 1,130 feet per second, which is quick, but it's not that fast, especially compared to light, for instance. So you may have been at a baseball game and seen the batter hit a ball, and you won't hear the sound necessarily right away. You'll hear it maybe a few milliseconds later, because sound is relatively slow compared to the light that you saw. So a good rule of thumb is for every foot a sound wave travels, the time required for that to happen is approximately 1 millisecond, or a thousandth of a second. So you can calculate delays and microphone placement, for instance, by using this simple formula. So if I'm recording an orchestra, I may have a pair of microphones behind the conductor. And if I were to measure the distance from those microphones, let's say to the percussion section in the back of the orchestra, that may be 30 feet or so, which is 30 milliseconds. But let's say I also have a microphone on the percussion only like 5 feet away from the percussion, or maybe 10 feet away at the most. In that case, the sound waves are going to hit those microphones first, and then it's going to reach the main pair behind the conductor. Well, a recording actually is going to sound better if we can delay back those close mics so that they arrive at the same time the sound arrives in the main pair. So by knowing the distances, we can calculate that we need to, in this case, delay those tracks, the close mic tracks, 30 milliseconds. And by doing so, we're going to get a much more phase coherent representation, and our stereo field will sound more homogeneous. So let's talk about the frequency wave of a sound, or the frequency of a sound. The frequency is simply the number of cycles per second that happen. So, sound is representing a vibration, and that vibration has a number of cycles per second associated with it. And the higher the pitch, the higher that number is. So there are different units that the frequency can be represented in: cycles per second, or you also find hertz. And hertz is represented by Hz, whereas cycles per second, just CPS. Humans can only hear a certain range of sound frequencies. From 20 to 20,000 is generally considered to be the greatest range that most humans can hear. And most of us can't hear that range. I know I can't hear up to 20K anymore. As you get older, you lose those high frequencies. And if you listen to loud music or damagingly loud signals, you're going to hear even less of the high frequencies. In fact, you're going to generally have a hearing loss represented around 4,000 cycles, because that's where the ear resonates. So anyway, let's getting back to the sound frequency range. Let's hear what this sounds like. We're going to have a sweep between 20 and 20,000 cycles. Now, I hope you're listening on headphones and not on your laptop speakers, because you're not going to hear the low frequencies very well on your laptop speakers, but you will on headphones. Here we go. So that represents the range of human hearing. Now, it really wasn't scaled perfectly, I noticed, but close enough. Let's also talk about the wavelength of sound. We mentioned this earlier. Wavelength is related to the frequency in the sense that you can take the speed of sound and divide it by the frequency that you're trying to find the wavelength for, and find the wavelength. Example here, a simple example is if you have a 1130 hertz wave, that goes exactly into 1130 feet per second once, and so that wavelength would be 1 foot. But looking at the range that we can hear, we can actually hear frequencies as low as 20 cycles, and that wave would be 56.5 feet long. So a very large wave if we could see it. And then at the other extreme, 20,000 cycles, it's just a little bit over a half an inch. And the wavelength is going to have various properties, or the sound's going to have various properties depending on the wavelength and how it interacts with objects in the room. And we're going to talk about that in a minute or two. Another thing that I should define is polarity. So a definition of polarity is simply when we have a wave, we have a positive and negative portion of the wave that's represented here. And if we basically invert that, so we have the negative where the positive was and the positive where the negative was, then that is a polarity reversed wave. So that's simply what polarity is. It's just making a mirror image of the wave and reversing the positive and negative portions of the wave. You'll find some people using the term out of phase, which is generally incorrect. And what they're really talking about is out of polarity. And you may have experienced this if you have loudspeakers that are connected to a power amplifier. You may have noticed that there's plus and minus leads coming out of the power amplifier. That are usually the plus is represented by red and the minus represented by black. And that, of course, should be connected to the same way to your speakers, which have plus and minus connectors. But if you happen to wire one side incorrectly, where you put the plus to the minus terminal on the speaker, for instance, and you play a mono signal through both of the speakers, you're going to notice that the sound is going to cancel out to a great degree because of the inverted polarity. If you listen to the stereo signal in that condition, what you'll notice is that there'll be a lack of low frequencies because they're canceling in space, and the sound won't sound like it's coming between the speakers anymore. It'll sound like it's actually outside the speakers. So when your speakers are out of polarity, it sounds really weird, and you should know when this condition happens and be able to hear it. It's pretty easy to hear once you've heard it. So one thing you can do when you get home is try this out and see what you experience, but I think you'd be very easy. It's very easy to hear when this happens. So let's talk about when we add together or sum sine waves, what happens. If we have the same sine wave and we add it in polarity, all we get is a louder sound wave. However, if we have the same sine wave and we add it to an out of polarity sine wave that's equal amplitude or volume, it will completely cancel out. So the way to think about this is that plus part of the wave adds with a negative part of the wave so that you get completely canceled amplitude. And this, of course, the same with the positive gets canceled with the negative of the wave. So I'm going to represent, or I'm going to show you how this sounds with music. Example here. This polarity demo, what I'm doing is I have Digital Performer here with two of the same exact waves. In this case, they're music waves from Nirvana, All Apologies. And so I just took one channel of that tune and duplicated it and put the one channel on top and the same thing on the track below. So we have two tracks, both exactly the same information, music. And I'm just going to do one thing and that's different to one of them, and that's to invert the polarity. So what's going to happen is that you're going to hear the music from track one on that first left fader. As I turn that up, you'll hear that track. And then I'll turn that down, and then I'll play track two, which is the second fader over. And then I'll turn up to track one again and then mix in track two to the point where I cancel out the signal from track one. So check it out. So that's track one. That's track two. Track one. And as I zero that so that it's the same level, it cancels completely out. Now if I mute one channel, it comes back. So it's just showing you that if you mute either channel, you still have the signal, but when both channels are equal level out of polarity, they completely cancel. So the point I'm trying to make here is that you don't have to have just sine waves to have things cancel. You can cancel complex waves too. In fact, we're going to do some more canceling here in a minute. But before we do, let's move on to a definition of stereo. So a stereo is defined as two discrete channels of audio played on two loudspeakers. So to have stereo, you have to have two loudspeakers or earpieces from headphones. But more importantly, you have to have different signal to each of those loudspeakers. So some of the information that's going to the left channel has to be different than some of the information going to the right channel. And in most music mixes, we do have some common information that's exactly the same for the left and right channels, and some information that's truly stereo that's different. So when we listen to music over speakers and if we're right between the speakers, the things that are exactly the same between left and right speakers sound like they're kind of hanging in space right between the speakers. And so the vocal will often be there, the bass drum, snare drum will often be there, bass guitar will often be there. But then there might be other elements like guitars and pan to the left and right, and pianos and other vocals. So try to become aware when you listen to music of where the instruments are placed in the stereo field, and notice how certain instruments tend to be in certain places. So we're going to do another polarity demo. In this case, we're going to do something a little different. We're going to use music that's stereo, and so we're not going to get complete cancellation because, remember, stereo's got something different on the left and the right channels. So that's not going to go away, but what is the same will go away. So everything that's panned to the middle or between the speakers is going to disappear. So that's called the mono component of the sound. So we have a mono component, which is what's being, it's equal in both left and right channels. And we have a stereo component, which is what's not equal. So first of all, let's just listen to how this sounds in normal stereo. This is from the Beatles' Revolver record, Eleanor Rigby. First in stereo.
Up the rice in the church where a wedding has been. Lives in a dream, waits at the window.
Okay, so that was the stereo mix. And if you're listening on headphones, maybe you paid attention to where the sounds were coming from. So that'll be a little clue as to what's going to happen when I cancel out the mono component. So let's take a listen to the same mix just in mono. This is not inverting the polarity of one channel. This is just adding left and right together so that both left and right have the same signal.
Look at all the lovely people. Look at all the lovely people. Eleanor Rigby picks up the rice in the church where a wedding has been. Lives in a dream.
So did you hear a difference? You should have heard a pretty striking difference between the stereo and the mono. And interestingly to me, I hear a difference in the mix or the balances, which is, I think, a very interesting thing that happens. But of course, you can hear the fact that all the sound is sort of like coming right between the speakers, and there's no sound really coming from left and right. So it's a mono signal. All right, so now we're going to do something that's even more interesting. And I'm going to do the same thing I just did, basically mono it out. But in this case, I'm going to invert the polarity of one of the channels. I think the left channel was inverted. And let's take a listen to what this sounds like.
Ah, look at all the lonely people. Ah, look at all the lonely people. Eleanor Rigby picks up the rice in the church where a wedding has been. Lives in a dream.
Well, that was interesting. Did you notice something missing? Well, hopefully you did, because the strings were completely gone. So you may have noticed when you listened to the stereo mix that the strings were right in the middle, but the voices were kind of panned left and right. So the voices were stereo, but the strings were mono. So when we inverted the polarity and added left and right together, the strings, which were mono, completely canceled out. So this is a really interesting thing to learn how to do on your own. And I'm going to show you how to do it. Well, I explained just now how to do it, but I'll have some demos on my YouTube channel of how to do it using Audacity and hopefully another DAW or two. But it's simply just canceling the mid channel out or the mono channel out by inverting the polarity of one of the channels and summing the left and right channels together. So let's talk about phase. Phase is different than polarity. There is one point where phase shift is equal to polarity. So when the phase shift is 180 degrees, that is equivalent to reverse polarity. But what phase is when you're really talking about the same wave delayed by a small amount, and that small amount has to be within one wavelength of that wave. And so what it looks like is just a shift like this, and that little symbol down there is the symbol that represents phase. And that shift can be from 0 through 360 degrees. At 180 degrees, you're out of polarity. So I want you to understand the difference between polarity and phase here. So phase shift is simply a small shift within one wavelength of the same signal. Also, you should understand what harmonics are. Harmonics can also be called overtones or partials. So musical instruments don't really have just one frequency. When you play a note on a piano, you're not just hearing one frequency. You're hearing actually many different frequencies. There is a fundamental pitch that you're hearing that we represent as the note value. But in addition to that pitch, you're hearing a series of harmonics or overtones that are related to that pitch. So what harmonics are is simply, if you know the fundamental of the frequency, let's say you're dealing with A440, for instance. Well, when you play A440 on a piano, what you're hearing is A440, but you're also hearing A440 multiplied times 2, times 3, times 4, times 5. And each one of those multipliers is a harmonic. So you got the second harmonic being 880, we're doubling of the original pitch, the third being 3 times, etc. So when we hear a piano note, we're not just hearing the one pitch of the fundamental, we're hearing a bunch of pitches. But we still hear it centered at the fundamental because our ear is very used to hearing this relationship between fundamental and harmonics. Looking at harmonics another way, you can see that there's the fundamental is got the lowest frequency, and then the second basically has two waves that fit into the first fundamental wave. The third has three waves. The fourth has four waves that fit into the same cycle. So the harmonic series goes all the way up, and you can hear partials as high as maybe the 13th or so, depending on the frequency of the note you're playing. We also will need to learn about timbre. Timbre, you could pronounce this timbre, but then maybe someone would think a tree is going to fall on you or something. So probably best to use timbre. So what it is the tonal quality of a sound due to its harmonics and envelope. Well, what's an envelope? It's not something you're going to mail something in this case. It's going to be how the sound amplitude changes over time. So we have some instruments that have very percussive envelopes, like piano or maybe a vibraphone or anything that's plucked or hammered. It's going to have a very quick onset of amplitude and in the envelope. Whereas if you have a bowed instrument or some wind instruments, they have a slower onset. That onset, by the way, is often called the attack portion of the envelope. So there's various portions that are defined of the envelope. If you're into synthesis, you may have heard of an ADSR in your synthesizer that controls the envelope of the waves that you might be creating in your synthesizer. And so there's attack, decay, release, and sustain, or sustain and release. And each of those really just represents a different part of the envelope. So anyway, the timbre is how we tell what is a guitar or what's a piano in a mix. For instance, if we're listening to some music, we can tell what the various instruments are because our ear is very used to determining, decoding these various timbres. So, but the envelope plays a big, very important part in our ability to be, excuse me, to be able to tell a guitar from a piano, for instance. So what I have here is an example of something I've manipulated the envelope with. See if you can tell what this instrument is. Do you know what that is? Well, it doesn't sound like it originally did because I changed the attack from being sharp to very faded in. So this is what it sounded like originally. And that's a lot easier to hear as it being a piano. Maybe you could tell from the overtones that it was a piano in the other example, but this way it definitely sounds like a piano. So this is just to show you that the envelope and basically how the amplitude changes over time is an important factor in determining what instruments playing. Let's talk about diffraction. This is a property of sound waves, and it's interesting because what it shows us is that sound waves can bend around obstacles or surfaces, barriers in this case. But that only happens when the sound wave is large enough so that it's larger than the barrier that is trying to block it. So in this example, we have a sound wave that's starting over there, sound source. And then we have this barrier, which is, you can think of as a wall, and that's being a little door opening in the middle. And as you can see, that sound doesn't just go straight as a beam out of that into the dark area. And actually, you have this the sound bending around the corners there a bit. And that's called diffraction. So when the sound wave frequencies are low enough that their wavelengths are large compared to the barrier, this is what happens. And if you're, one example of this might be if you were listening to a band at a club and you went outside to get some fresh air. And let's say you were just going to have you went out and put your back against the wall in the dark area outside the club. You would still hear the bass guitar pretty clearly, but some of the cymbals may not be as loud as they would be if you're standing right in front of the door. Because the bass guitar, being low frequencies, would bend around and the higher frequencies wouldn't. So those low frequency waves can diffract around corners. But as I was saying, if we were listening for the cymbals, those cymbals tend to have high frequency waves. And in that case, we can have what's called an acoustical shadow. So what we're showing in this example is a sound source on the left of this head. We're looking down on a head here. And you can see the sound hits the left ear but on the right side of the head, it doesn't really get to the right ear because the head is actually blocking the sound waves. This only happens when the frequencies of the waves are high enough so that the wavelength is shorter than the size of the head. So this effect is called shadowing because it creates an acoustical shadow. In other words, a zone where you don't get the sound. So just similar to what would happen if you were standing outside and you're creating a shadow from the sun, for instance. To remember, the thing I want you to remember is that this only happens with short wavelengths or high frequencies. Another thing you should be aware of is what's called a masking effect. Now, this is an interesting phenomenon. We've all experienced it, probably been in a noisy bar or restaurant where there are a lot of people talking, and it's hard to hear the conversation at the table because all this noise is coming into our ears other than the conversation we're trying to listen to. And oftentimes we end up having to watch people's lips and sort of read their lips. And this happens because there are a bunch of voices happening that are basically in the same frequency range of the voice you're trying to hear, and it interferes. So you only hear clearly a voice if the voice is significantly louder than the other voices. If it's close to being the same volume, then it's really hard to hear a voice that's about the same volume as the background noise. And the reason that's so is it really relates to frequency. So when you have two frequencies that are very close to being the same and one is significantly louder than the other, the louder sound will mask or make inaudible the softer sound. So this is what we call a psychoacoustic effect, and it's actually used to get rid of information for compression in like MP3s, for instance. So they figured out that, there's certain frequencies you're not going to hear in a musical signal because they have this relationship of being too low compared to another frequency that's louder. So you can't hear it. So they actually throw that information away. And that's how you can get smaller file sizes out of MP3. So a typical MP3 may be 1/6 of the original file size. So they've thrown away a lot of the information based on the fact that supposedly you can't hear it. But we all know, I think, that MP3s are not perfect and they have quite a few problems, actually. But anyway, that's the technique they use, is by using the masking effect. They actually get rid of signals supposedly you can't hear. So let's listen to an example of the masking effect. And in this example, we're going to hear what the MP3 distortions do to a sound wave or musical waves. You don't normally notice them because they are masked by the louder signals. But in this case, we're going to do something that's pretty much exactly what we've been doing with cancellation. And we're going to cancel out the mono component of an MP3 file. And when we do, you're going to hear all the distortions and what I like to call phase monkeys or space monkeys that are distortions in the MP3 signal. So first we're going to hear a Bjork track in normal PCM stereo, which means it's not compressed, and then in stereo. And then we're going to listen to it in mono, once again, uncompressed in mono. And so you'll hear everything that's in the center dropping away. And then we're going to compare that same scenario, but not with an uncompressed signal, but with a MP3 192K bit rate. So here we go. All right, so that's normal stereo. Here comes mono. Sounds okay. So this is left and right mixed together. Out of polarity. Notice that it sounds really different because a lot of it's canceling out in the middle. So you can hear her voice, but it's mostly reverb, which happens to be stereo. Okay, so that was PCM, uncompressed audio, mixed to mono and then one channel inverted polarity. And now we're going to listen to the same thing, but with an MP3. And you're going to hear the artifacts of the compression. Sounds a lot different, doesn't it? That's pretty bad, huh? She sounds like she's drowning. Anyway, so it sounds distorted and phasey. Why? Well, this is why. Because the mono component which is what's common between left and right, is no longer masking the distortion caused by the mono component or the discarded data. So the moral of the story is that MP3s come with a lot of side effects. And oftentimes these days, there's no need not to have MP3s as long as you have enough storage space on your computer or whatever. You can download full resolution uncompressed files in the form of FLAC, FLAC file types, or there's also Apple Lossless and a few others that they do reduce the data size probably about in half, but with no loss. So consider using those formats instead of MP3s whenever possible. All right, let's also talk about how we can hear sound and the direction of a sound in space. As it turns out, we have the ability to actually localize sound to a pretty high degree, which is to say, if we were in a dark room, so we couldn't see anything, and somebody spoke, we could point pretty much to where they are in that room and turn on the lights, and pretty much our fingers would be pointing right at that person, plus or minus maybe 5 or 10 degrees. So how do we do that? Well, we use our ears, of course, and our brain. And one of the ways we do that is simply by the difference in intensity between our ears. So if a sound is coming from the left of our head, it's going to be a little louder in the left ear than the right ear because, sound loses intensity with distance. So if we snap our finger to the left side of our head, we're going to hear the sound a little louder in the left ear than as compared to the right ear. Also, there's a difference in time arrival. The left ear will get the sound before the sound reaches the right ear. Now, this is a very short delay difference, but we can actually, at certain frequencies, detect this delay. And I have an example of the presence effect that you can check out on my YouTube channel that demonstrates the fact that you can get things sort of to pan left and right without changing the intensity at all, just by changing the time. So the time arrival makes a difference. Also, our head at high frequencies, as we showed earlier, can shadow frequencies. So when we snap our fingers to the left side of our head, the snap sounds different in the left ear as compared to the right. What really happens is that we have more high frequencies coming to our left ear than the right ear. And that timbral difference we can pick up, and that helps us localize the sound as well. We also have this pinna on this fleshy part of our outer ear, that part that sticks out from our head. And it reflects sounds differently depending on where angle they're coming from. So if they're right in front of you where you're looking, that reflects in a certain way. But if they're, at different points on the lateral plane, they're going to sound slightly different because of the reflection compared to the direct signal going straight into your eardrum. There's also sound reflecting off your outer ear, and that creates a short delay that you can hear being different at different angles. So even with one ear, we can localize sound to some degree because of having that reflection off our pinna. So try to become more aware of how you hear sounds in space, or the direction of sounds in space. And you might also try some of these experiments where you apply a delay to the same signal being fed into the left and right speakers, for instance, and see what happens to the localization of sound. Or maybe you can use an equalizer to take out high frequencies and see, if this actually makes a difference when you listen in stereo on your computer, for instance. All right, we also need to talk about loudness and decibels. So we all hear sound as having a certain intensity or loudness. Decibels are simply a unit to represent that. Decibels can represent the perceived intensity of a sound, acoustic sound, for instance. But the thing to know about loudness is it's not a linear effect, which means that we don't hear a one-to-one relationship with intensity. So if something is twice the intensity of something, in other words, we have a person talking and then another person starts talking, generally it doesn't sound twice as loud. If it did, that would be a linear relationship because it'd be a one-to-one relationship. But that's not really how we hear. It's similar to how we hear musical frequencies. We know that when we play an octave, we're doubling the frequency. Well, it doesn't generally sound, we wouldn't say that's twice as high as the original frequency. That's kind of a hard thing to quantify anyway, is that, doubling a pitch, how much higher is that, subjectively? Well, it doesn't sound twice as high generally. We wouldn't say that. And the same is true with volume. Something has twice the intensity, it doesn't sound twice as loud. So we don't hear it in a one-to-one or linear relationship. So what we did with the dB or decibel units was we scaled them to what's called a logarithmic scale. And what that does is simply takes this huge range of intensities that we can hear and scales it down to more meaningful units. So what you need to know is that for every doubling of acoustic sound intensity, there's only a 3 decibel increase in loudness. So, for instance, if one person is clapping and another person starts clapping at the same volume, that's 3 decibels. And then to get 3 decibels more, you now have 2 people clapping, right? So you have to double that, so that would be 4. And to get 3 decibels more, you'd have to double that, which would be 8 and 16 and 32 all the way up, 64, so on. So you only get a 3 decibel increase every time you double the acoustic intensity. As I said earlier, we can hear a huge range of intensities, a trillion to 1. And so we would want to deal with those kind of numbers. We need to have something scaled down to what is a lot more meaningful, and that's what the decibel does. And that's why it uses a logarithmic relationship. And the logarithmic relationship is simply this relationship of doubling. And you'll find that relationship all throughout acoustics and music because a lot of our hearing is related to logarithmic functions. So the units of the decibel can measure intensity of not only acoustic waves, but also electrical waves. So when we look at a meter in a mixing console, for instance, what we're looking at there is electrical waves. And specifically a portion of the power, which is called voltage. So we're looking at what's called a voltage, and which is representative of the intensity of the sound that's going into the meter. And the sound wave in a mixing console has been transduced from acoustic to electrical energy. And we're going to talk about transducers in the next lecture. So dB can be represented as dB SPL, sound pressure level. That's what SPL stands for. Also, it can represent voltages on a meter. A dBV is a voltage, a unit of decibels. So if you look at meters on your mixing console, for instance, you might see them represented as decibels. They can also represent power, which is a dBm, is a unit of electrical power. So some definitions to know about decibels. So how they defined the decibel was that 0 dB represents the threshold of hearing. This is where a large sampling of people, when they measured them, they could start to hear a sound. So they played a very low intensity sound wave into their ears, and then they raised their hand when they could hear it. And when they did it across a large number of people, they came up with a value, an intensity that they relate to 0 dB SPL. So 0 dB is just defined as that point at which you start to hear a sound, if you have good hearing. And then at the other extreme, we have 120 decibels, which is generally considered the threshold of pain. Now, this is, of course, variable. It depends on what you're listening to and the frequencies. But when you get up to that level, it starts to get painful, or maybe it already is very painful. You can also calculate the dBSPLs by knowing the change in intensity. So what that equation is, 10 log times P over P reference. What that refers to is the reference is where you were initially. So if you had one voice speaking, that would be 1. And let's say you had 2 voices speaking, and you want to know how much louder that is. So that would be 2 as a numerator and 1 on the denominator. And so that's 2, and the log of 2 is 0.333 times 10 is roughly 3 decibels. So that's how you can determine decibel values. You won't have to do that for class. I just want to point this out to the people that are a little more technical. You do need to know that when you double acoustic sound pressure, it's going to be 3 decibels, however. And you also have to know that when you do the same thing with signals going to a meter, it's not 3 decibels, but it's actually 6 decibels because we're dealing with voltage in that case. And you notice that when we're dealing with voltage, the equation's a little different. So rather than having 10 in front of the log, you have 20. So it's actually twice as much as the acoustic sound pressure voltage doubling is. So if you double the amount of signal going to a meter, it's going to be a 6 decibel increase, which is what I'm saying right here. So just know this. Remember that this is the case. 3 decibels when you double the acoustic energy, and 6 decibels when you double the voltage as you would going into a meter, for instance. We all know that sound intensity diminishes with distance, but there's actually an equation or relationship that's pretty simple, really, which is that every time you double the distance, you lose 6 decibels of sound pressure level. And this doesn't really hold for inside buildings or rooms because you get reinforcement from the room itself. Concert halls are actually designed to reflect sounds to the listener. So you don't get as much transmission loss in a hall, for instance, or even a normal room as you would outdoors, for instance. But outdoors, this relationship holds pretty well. And you can calculate how much loss you're going to have with different distances. Another really important thing to understand is that the perception of loudness changes with listening level at different frequencies. And what I mean by this is that when you listen to music at a low volume, the balance between the low, mids, and highs changes perceptually. It doesn't really change if you were to measure it, but to our ear, it sounds as if the very low and the very highest frequencies are diminished as we turn down the sound and become more equal as we turn up the sound. And you may have heard the Fletcher-Munson curves that basically they graph this effect out at different listening levels. So the take-home message here is that you have to be aware of this as a mixing engineer or producer, and that when you listen in the control room, you want to at least at some point listen at the volume you think that most people are going to be listening at, because your decisions on how much bass frequencies to add to the bass guitar, for instance, and how much EQ to use in the cymbals, for instance, will be affected by the volume at which you listen to the signal, your mix at. So you don't want to listen too loud and make all your decisions at a really loud level, because when you start listening to it at home at a reasonable level, you'll find that you don't have enough bass or high frequencies. You probably have on your stereo, if you have a stereo at home, a button that's called loudness, and when you push that button, you may have noticed that it boosts the low frequencies and high frequencies. And so the point of that is to, when you're listening at low volumes, to restore the frequency balance that's lost because of this effect. So this is another psychoacoustic effect. It isn't measured by instruments, it's measured by our perception. And we don't perceive these lows and high frequencies being equal at all listening levels. At low levels, we tend to lose the low and high frequency signals to some degree. So we hear actually we have the most sensitivity around 4,000 cycles. So that's sort of the reference point. And that's because our ear canal and our ear resonates at that frequency. And that ends, by the way, that tends to be where a lot of speech intelligibility lies. And the consonant sounds, for instance, that define, the beginnings and ends of words, for instance. So it's important as an engineer producer to know that listening at different volumes is going to affect your sense of how much EQ or frequency adjustment you might want to apply. So I'd like you to make this as interactive as possible for yourself and try some of this, and then we'll talk about this in class. But I think you can have a lot of fun trying to cancel out your own music with the techniques that I described, cancel out the mono component. And I find this really useful, actually, in listening to what they did with stereo effects in particular, and reverb and that kind of thing in a mix. If you cancel out the mono component, you can hear those things very readily. So it can kind of let you look under the hood a little bit more in a mix that you may be familiar with. You'll hear it completely differently when you do that. So try that out. There's also a demo about the Haas effect. This is basically how you can get the signal sort of to sound like it's coming from more the left or right speaker simply by delaying one side. And also try listening at your speakers at low volumes and how the tonal balance changes as you turn it up. Get aware of how that is in effect. Also, if you have an iPad or smartphone of any type, there's free apps that you can download that will read out decibels for you. And it's kind of interesting, important to understand what typical background decibel levels are in spaces like your home or in your car, for instance, or when you're listening to music, what levels you normally listen to music at. So I encourage you to download those apps and try that out. All right. Well, I look forward to talking to you about this in class.